Welcome to the Deep Dive, where we take a mountain of information and distill it down to the essential, surprising nuggets you need to know. Today, we're embarking on a really crucial journey for anyone aspiring to command the skies. Imagine an aircraft, a marvel of engineering, gracefully soaring through the air, constantly battling unseen forces, yet somehow remaining perfectly safe. For you, preparing for your ATPL theory exams, understanding why that safety is maintained, what limits are at play, and how the very structure of the aircraft interacts dynamically with the air isn't just important, it's absolutely fundamental.
Oh, absolutely. It really is about truly understanding that invisible dance between the air and the airframe. The underlying design choices, the hidden strengths, and those critical boundaries that keep everything working, well, in harmony.
Precisely. Our deep dive today explores the critical world of aircraft operating limits, structural integrity, and the fascinating, sometimes quite counterintuitive, realm of aeroelasticity. This is precision engineering, really, at its finest. Our mission is to unpack the core definitions, maybe demystify some complex relationships, and extract those essential insights, those nuggets that will equip you not just to pass your exams, but to genuinely grasp the why behind those crucial airspeed and load factor boundaries. So let's try and unravel that invisible dance. Right, let's begin by exploring what we're calling the invisible boundaries. A deeper look into aircraft speed limitations and the forces, or, the loads, they're designed to withstand. Every aircraft is built with specific operational boundaries. That's to ensure safe flight. And these aren't arbitrary numbers, are they? They seem to stem from really fundamental engineering principles. From your perspective, what are those foundational considerations that dictate why these limits exist in the first place?
Well, what's truly fascinating here is how it all kind of boils down to three interwoven pillars, if you like. There's the inherent strength of the aircraft structure itself, its stiffness, and crucially, the assurance of adequate control throughout the aircraft's entire operational envelope. When we talk about strength, it's simply the ability of the structure to withstand all the anticipated forces and loads it will encounter during its lifespan without actually breaking. It's about how much stress it can physically take before it fractures.
Okay, so it's not just about holding up the static weight of the plane on the ground, but handling all the dynamic forces, every twist, every turn, every bump in the air.
That's exactly it. And then we have stiffness. Now, stiffness refers to the structure's resistance to deformation or bending when it's under aerodynamic loads. You see, a structure that's too flexible, that can lead to some really serious problems. Things like aileron reversal, flutter, divergence phenomena we'll certainly get into later. The aircraft has to be stiff enough to prevent these undesirable occurrences from ever happening within its permitted speed range. It's non-negotiable.
And the third pillar you mentioned, maintaining adequate control, that feels pretty intuitive, I suppose. I mean, no matter how robust or rigid an aircraft is, if a pilot can't effectively maneuver it, you've got a fundamental safety issue right there. So these limits are clearly in place for very sound engineering and safety reasons.
Okay, now let's move into understanding the specific loads, the critical concept of safety factors, and what I sometimes think of as the weight dilemma in aircraft design. Right, and this brings up a really critical point. How do engineers actually quantify these loads? We have two key terms here, limit load and ultimate load. The limit load is the absolute maximum load the aircraft structure is expected to encounter during its service life under, normal specified operating conditions. This includes the typical maneuvers you might perform and the sort of turbulence you'd expect to fly through. Think of it as the highest stress point you'd anticipate hitting during regular but sometimes demanding operations.
Okay, the expected maximum and the ultimate load. That sounds much more final, like the absolute breaking point.
It is, precisely. That's the actual load at which the structure is expected to fail or fracture. It's the very edge of structural integrity. Now, the critical relationship between these two is the factor of safety. This is defined simply as the ratio of the ultimate load to the limit load. It's essentially the margin of safety built in beyond those expected operational limits, a buffer, if you will.
Okay, so what is that safety margin for aircraft? Is it?
All right. Many thanks for listening to this free part of the ATPL Theory podcast. If you want to continue learning and access the full comprehensive guide, go to my Patreon at patreon.com/ATPLtheory or my Hero at herohero.co/ATPL. That is patreon.com/ATPLtheory or herohero.co/ATPL. Wishing you all the best.